So on Friday we introed our thermochemistry unit, talking about how all substances have kinetic energy, which is dependent on their velocities, the velocity, the speed of the molecules in the substance, as well as the temperature of the substance, and how those things are all directly related. And we use this knowledge to do some models and talk about heat transfer at the molecular level and at the macro level. But that was all qualitative. Okay, we said heat flows from my hand to the cup, or from the water to my hand. What we want to now be able to do is to quantify it and be accurate in our representation numerically of this heat transfer. So in order to do that, we have to define two things. We have to define a system, and we have to define a surrounding. Okay. So, for example, in the activity we did on Friday, we had two hands. One hand that was in hot water, and that was hot, and then we had another hand that had been in cold water, and as a result was cold. And then these hands were shook. Okay, and so what happened here is we know the heat flowed from hot to cold. So heat flowed from the hot hand into the cold hand, which caused the person whose hand was in the hot water to feel colder, and the person who's in the cold water hand, this one, to feel warmer. So what's interesting here is the perspective that we take is going to change the sign of the heat flow. So for example, if we talk about the perspective from the person who had the hot hand, they started with a certain amount of heat and they lost heat. So the change in the amount of heat was negative. They lost heat. However, from the perspective of the person with the cold hand, they gained heat. They felt warmer. So to them, if we look at it from the perspective, if we look at the heat transfer from the perspective of the cold hand, the change in heat was positive. So to make, this could mess up some calculations and could alter how we make certain assumptions about reactions. So in order to avoid this, we have to define the system and the surroundings. So for example, if we said the hot hand is the system, okay, let's say the hot hand is the system. Okay, and again, these are just terms that are arbitrary. They can be defined for any reaction. So if the hand here is the system, that means that everything else in the universe, everything else besides the hot hand, is considered the surroundings. So everything out here would be the surroundings. Okay? Because now when we talk about heat flow, we're going to talk about how heat flows between the system and the surroundings, between these two things. Okay? So, if we define the hot hand as the system, everything else is the surroundings. That means the cold hand would be considered part of the surroundings here. Okay? And we want to know, how did heat flow? Well, it flowed from the system, the hot hand, to the surroundings. Okay? Since the hand lost heat, we can call this an exothermic reaction. The system lost heat to the surroundings. Okay? On the other hand, let's say here was the hot hand, here was the cold hand, and now let's say we define the cold hand as the system. That means everything else is the surroundings, okay, including the hot hand. Okay. So now from the perspective of the cold hand, as the cold hand was touching the hot hand, it was gaining heat. So heat was flowing from the surroundings into the system, the other direction. Since the system gained heat in this case, this would be an endothermic reaction. Okay? And the easiest way to think of this is endo meaning into, so heat went into the system. Whereas here heat exited the system. It went from the system to the surroundings. Okay? Notice here, the system and the surroundings can't both gain heat, or the system and the surroundings can't both lose heat. This is essentially what the first law of thermodynamics is. It's the idea that first law of thermodynamics, energy cannot be created or destroyed. Heat cannot be created or destroyed. It can change forms, but it can't be created or destroyed. So in order to measure this, we have to compare the initial amounts and the final amounts of energy in these reactions. Okay? And this is called the internal energy that we're going to introduce. U is the internal energy, all of the energy of a system, internal energy. And so if we want to measure how much energy changes between the systems and surroundings, we're going to measure the delta U, the change in U, the change in internal energy. So one thing to note, since the system and surroundings can't both gain heat, they both can't lose heat, we know that the change in energy of the system plus the change in energy, internal energy of the surroundings, is always going to equal 0. So think about this, right? If we had our hot hand and we had our cold hand, okay, and we define the hot hand as the system, we know that the hot hand is going to lose heat. Okay? This number is going to be negative. At the same time, the surroundings, the cold hand, is going to gain that same amount of heat. So let's just say the system lost negative 10 joules. Remember, the units for heat are going to be joules, and for energy are going to be joules. That means that the surroundings is going to gain 10 joules, the same amount. Heat can't be created or destroyed. So the net change between the system and the surroundings is always going to be 0. We can break down internal energy further, okay, because internal energy is going to be equal to the amount of heat transferred. Q is heat, okay, plus the amount of work done in the reaction. Okay, work, if you remember from physics, is equal to, work is equal to force times distance, displacement. But we don't need to worry about that. You don't need to know where these variables come from, how this equation arises. We just need to know that the change in internal energy is equal to the heat transferred plus the work done. And we'll most constantly deal with a constant pressure system where work equals negative P delta V. This is negative pressure times the change in volume. So now if we do a little substitution, we'll get that the change in internal energy of a system is equal to the heat transferred by the system minus pressure times the change in volume. The way we use this equation is we have to know a few sign conventions. Okay, so if work is done by a system, okay, so by a system, if the work is done, by the system, that's always going to be considered negative. If work is done on the system, that is going to be considered a positive value. If heat is absorbed by the system, endo, so if the system absorbs heat, that's going to be considered a positive value. And if the system loses heat, exo, that's going to be a negative value. So just a very quick example. Let's say we have a tank here with a gas in it and a piston. Okay. There's a gas floating around. We have some gas molecules moving around. They have some kinetic energy. And let's say we lower the piston. We push the piston down until it's right here. Okay. In this process, we did work. If we define the system as the gas in the tank, we did work on the system. We pushed the piston down, we did work on it. So the amount of work that we did would be positive. So this value that we would plug in for W here would be positive. Okay. In addition, we're giving heat to the system. That's an endo reaction. This would be a positive value too. We'll play around with this more in class, but what you need to walk away with here is these sign conventions and knowing and feeling comfortable with these two equations, and endo and exothermic reactions in regards to how heat flows between the system and the surroundings.